Hey everyone, so welcome to the last bit of ME 160. This is a continuation from the first discussion on vibration absorbers or June mass dampers. I would advise if you haven't seen that lecture, go to that first because we'll be assuming some things that was already discussed in that previous lecture. So by this point, we should have a good idea of what vibration absorbers should be doing. And we now want to essentially optimize or find out what sort of properties we want for our absorber. And not only that, we will start to discuss what we call the safety bandwidth or the um, zone of operation for our tune mass damper. Let's not forget vibration absorbers. These are essentially second degree of freedom attachments to our systems, and their purpose is to take away some of the energy due to vibration at a specific frequency range. Now, the application can range from electric wires to structures and whatnot. The most famous one is, of course, the one in our title card, which is the Tune Mass Damper of Taipei 101. So, just to review again, vibration absorbers, of course, they are second degree of freedom elements. When you attach them to the main system, they tend to take away most of the shaking for a particular frequency range. And we have to keep in mind that this is, of course, a two degree of freedom system, meaning that the properties that both the main system and the absorber on its own is completely different from what the properties will be when you combine them. So we have to keep this in mind. The primary system and the absorber itself will have their own distinct single degree of freedom properties. And once you combine them together, particularly for the system characteristics, they will change. The primary system's natural frequency will no longer be the natural frequency of the combined system. In fact, this will actually be completely new. So just keep that in mind. And while we're doing so, we're actually still going to be using some single degree of freedom properties from both of our systems. This can get a little confusing at times. So whenever you're viewing a vibration absorber lecture or any reading any module, it's good to have a sort of reference sheet for the equations in mind. So this slide in particular is at least meant to elucidate or at least clear out whose property these characteristics are. So now, okay, let's go to the meat of our topic. I believe we've already discussed this in the previous lecture, but just in case, this is the magnification of the primary system, or this is essentially the normalized amplitude of our primary system. Now, the primary system is the one that we want to protect. So essentially, when this system encounters a vibration in a particular frequency range, we want the magnification, this MP, to be as minimum as possible, to be as minimal as possible. Now, if you look at this fraction, it may not be obvious, but there is already one way that we can achieve that. And this fraction itself becomes minimized if the numerator becomes 0. So the moment that this term is true, or at least becomes 1 equals r sub a, then we achieve 0 amplitude. Now, keep this in mind. We are assuming that there is no damping for either the absorber or the primary system. So this is only true for that case. Just keep that in mind. So when r sub a is equal to 1, that means our magnification for the primary system is 0. And what is RA? It is the ratio of the forcing frequency from the disturbance over the absorber's single degree of freedom, natural frequency. So in order to kill the vibration, we want to match the absorber frequency to the forcing frequency. And that is the mathematical goal of the absorber, is to match the forcing frequency. Now, if you look at this fraction here, there is also a danger. So if the numerator holds our heaven, our paradise, the denominator holds the greatest danger. What do you mean by the greatest danger? If this denominator ever descends to zero, then this magnification will blow up to infinity. So what could be the values that cause this massive blow up? This massive blow up, if you manage to solve for the forcing frequencies which trigger this exact equation, you'll actually get the two natural frequencies of your combined system and absorber. Now, given this case, there are two conditions. Keep this in mind. So it's possible that the forcing frequency, the omega here, is actually equal to the primary system's natural frequency. So it could be that there is a design mistake or there is an unavoidability when choosing the frequency range. So you have no choice. You have to operate at your primary system's natural frequency. So in order to destroy or at least minimize the amplitude of your primary system, you target the omega A, the absorber frequency, to the forcing frequency. And by coincidence, that forcing frequency is also the primary system's natural frequency. And there are implications to this. So first and foremost, your single degree of freedom frequency ratio is immediately equal to 1, which reduces this fraction or this expression here. Your R's are also the same, they're equated, and you get this simplification. Now, there are also cases wherein the forcing frequency is not related or is not equal to any of the single degree of freedom frequencies. By this case, the absorber just targets the forcing frequency while ignoring the existence of the primary frequency. Now let's talk about the what we call the safety threshold. The safety threshold is kind of like a operational bandwidth. It's the safe zone uh, that the absorber can kind of safely operate the system in. Rather, it's kind of the reverse. It is a safe zone for the primary system given a particular absorber. So if we graph the magnification of our primary system with respect to the primary frequency ratio or P, we will get this graph, this green one here. So this green one here has a mass ratio of 0.1 and has a beta of equal to 1. And what you notice here is that there is a dip. Instead of having one infinite mountain here in the middle, which is typical of a single degree of freedom system, you have a valley. You have a safe zone and it's bordered by two massive mountains which lead to infinity. And your goal here is to keep your device, your system, operating in a zone where the magnification is acceptable to you. Now, this zone, as you can see here, denoted by these blue dots here. So it goes from here to here. This is what we call the safety threshold or the operational bandwidth. If you switch on your machine, it will start from here and then reach the target operating frequency. It's okay for the machine to land at an instant at its natural frequency as long as it doesn't stay there. Now, if you want your machine to stay at a steady frequency, this is where the magnification starts to matter. So this is essentially, this quantity here describes where the safe magnification is during operation. And for this course, in order to keep things a little easy and for us to get a hold of how this quantity behaves, we will just assume that our safety or safe magnification has an absolute value of 1. So this is going to be our assumption. Again, in the industry, this will not be the case. This is just for the sake of trying to get a hold of what exactly the safety threshold is as a property. Now, for the rest of this lecture, I want you to pay attention to this valley here, this shaded area here. We're going to modify some of the properties here, starting with the mass ratio. So right now, the mass ratio is at 0.1, it's 10%, meaning that the absorber is just 1/10 of the primary mass system. Um, Perhaps you'll be curious, what happens if we reduce this? What if we reduce our absorber mass by 5%? So if we do that, we get this. We get a sort of narrowing of our operational bandwidth. And we can ignore this for now. I have no idea why I generated this in the first place, but you'll see later. As you can see here, the moment we reduced our mass ratio, the safety threshold kind of shrunk. Now, what happens if we increase the mass ratio? I mean, what if we made our absorber heavier? So, of course, the opposite is going to happen. It's going to open up. The higher your mass ratio is, as you can see in this graph, so the purpose of the graph is, in fact, to show the relationship between RP and the mass ratio. If you increase mu here, this safety zone will just keep growing and growing. And in this graph, as you can see, it just keeps growing and growing, this gap here. So you might be tempted to think, okay, so that means all I have to do is to make my absorber heavier and heavier, then it's going to be safe in plenty of operational frequencies, right? So is that all that matters? Actually, there is a limit. So in ME160, the limit is not as obvious. So of course, if you pick something a little too small for the absorber mass, it's going to be too ineffective. However, if you pick anything that is too heavy, like more than a quarter of the primary system, other things start to play its part. So, like for example, perhaps the absorber becomes too heavy statically or structurally for your primary system. So, an example of this is, what if you want to make a building safe from earthquakes? And to do that, you make an absorber, a giant steel ball that is as heavy as the building itself. Can the structure support such a thing, even though technically you'll be completely safe? So that threshold would be way beyond this graph. So just imagine it, making a steel ball that is as heavy as a building and then hooking it up to the building itself. Won't the building just collapse? So we do put in a limit to the mass ratio or the absorber mass. We want it to at least stay below a quarter of the primary system's mass. So this is for the structural purpose. This quantity is again not visible to ME160 analysis because we usually ignore structural integrity, but we do have to keep this in mind when we're in practice. So with that, let's look at an example. So as you can see here, this is a compressor. So this is a yellow compressor. It's on a table. Now, this compressor is being exposed to a 400 Newton fully reversing force. And that force actually comes from itself because the manufacturer perhaps had an issue with balancing the components inside the compressor, or maybe it was damaged in transport. So either way, the compressor is generating its own bad forcing function. So that amplitude is 400 newtons and it's operating at 1600 RPM. Now the compressor plus the table, and they weigh 60 kilograms. And now we are being asked to design a tune mass damper such that number one, it completely destroys any system vibration caused by 1600 RPM and 400 Newton amplitude. The second is we want to allow only a maximum absorber deflection of 2.5 mm when exposed to the disturbing frequency. So the second one is, the first one is actually the thing that all absorbers do, and the second one is quite specific to the circumstance. Now, as usual, before we start solving anything, we want to sort out the given so that we can have a little bit of clarity. So first, Let's sort out what belongs to the primary system. It just happens we only know the weight, the mass of the primary system. Next, for the absorber, we don't know much except that the maximum deflection, the maximum X of our absorber should be 2.5 mm. As for the excitation, these are what we know, 400 newtons. Right now, we don't know what 1600 RPM is exactly. So is this all that we can do? Actually, there's a problem here because we don't know what 1600 RPM is. And also, we don't know any properties for the absorber. Like we don't know its mass, we don't know its stiffness. So where are we gonna do? So for these cases, if we do not have any other indication, it is safe to assume that this frequency here is actually the natural frequency of the compressor. What's the basis of this? Um, there's really no other basis here. It's kind of like, okay, so this is all I'm given, and this assumption will allow me to move on with my solving process. It's just that it's an educated guess, essentially. So what we have is actually this condition, omega is equal to omega p. Now this is only possible when we are in the first condition. So for the first condition, all of our omegas pertinent to the absorber system should be equal. So this is the first case. Excellent. So now let's move on to the actual solving process. What do we need to look at first? Let's look at the second bullet here. We are given a maximum deflection of our absorber. So we have an equation for XA actually. Here it is. And our condition here is that it has to be at maximum. So when is this at maximum? This is the thing here. When is this quantity at maximum? So of course, it's going to be at maximum when uh, actually not quite. This is not going to be the maximum. Sorry, um, scratch that. So this XA at a particular instance at a disturbing frequency is going to be 2.5 mm. So what we're going to do is we're going to equate all of our omegas here to 1600 RPM. And if you look at the case here, you have Ka minus Ma omega squared. If you insert omega here, which is essentially omega A, you essentially end up with Ka minus Ka. So this becomes 0. The only thing that will be left in this denominator is this quantity. And this quantity is Ka squared. It's going to cancel with the Ka at the top side. So Xa here at omega equals omega p equals omega a will devolve into this form. Oh, okay. So is this it? Yeah, that's all it is. So this only happens because we are looking at the disturbing frequency that we want to kill. And it so happens that this omega managed to knock out an entire term in our denominator. So in this case, we only have one unknown here, which is Ka. Let's go. We know Xa, we know F naught. And if we substitute, you get this stiffness for our absorber. And since we have a stiffness for the absorber, we also have the frequency of our absorber, we can get the mass of our system. So this is the mass of our system, essentially. Nice. Oh wait, sir, why is this Ka over omega p squared? This is a safe equation because again, all of our omegas, just for this problem, equated to each other. Now, is this okay? Not quite yet. We have to check if our mass is within spec of our mass ratio limits. So we take mu, we take the mu of our system, and then we check. So is this mu within 0.05 and 0.25? Yes, it is. So essentially, we are good to go. Now, this is what our magnification versus RP looks like. So it kind of looks like our generic example. Our mu here is very close to 0.1, so the graph kind of looks the same. As you can see, we already marked where the safety threshold is. So when are we gonna be solving for the safety threshold? We're gonna solve it very soon. So now this extension of the previous example is asking us, okay, where is the safety threshold if our conditions for safety is that its magnification should be of magnitude 1 or less. Now, uh, here we have to be mindful of the definition of this sentence. If we translate that into math, this will be your equation. So you are safe as long as this is true. However, this is an absolute value function, meaning there are actually two functions hiding within one line. So we have to extract both of those equations. What do I mean by this is essentially two equations in one? So let's look at this from the positive and the negative side. So if this MP is positive, essentially just remove all of the bars and you get this plain equation here. However, we can also have negative MP here. Negative MP, the absolute value of that is less than or equal to 1. So the converse of that will be this. Your MP should be greater than or equal to negative 1. So both of these conditions must be true. Now, since we're solving for the operational bandwidth, we have to look for the omegas that denote the safe zone for our system. So by having these equations, the next step then is to find for the omegas that fulfill the borderlines of these equations, meaning we have to find MP is equal to 1 here for this equation, and then we have to find MP is equal to negative 1 for this equation. So we end up having to manipulate this equation here. Oh, what happened here? Since we are having a case 1 problem, the beta disappeared and our r's essentially became equated to each other. So we have a very reduced function here. And for the negative side here, MP is equal to negative 1, we get this. Now you may be surprised. The roots of these equations are quite different. So for example, here in the positive side of our absolute function definition, if we want to look for the omegas that fulfill this kind of function, the border of this function, we get this. So omega B2 meaning it is bandwidth 2 is equal to the absorber frequency multiplied by the square root of the mass ratio plus 1. So this results eventually in this. Now, how about this one? This one becomes essentially a quadratic function. Unfortunately, it does not reduce just like this one. And what we end up with is actually three, or rather two roots here. There is one root, which is the other side of our bandwidth. And then there is another part, the outlier, which is not included in our bandwidth. So that means there are essentially three answers. I thought the bandwidth should only be bordered by two values. So you're correct. There should only be two omegas that are valid for this case. The other one is extraneous. It's not, it fulfills this condition, but it's not part of the safe zone. So we're going to show that graphically in a little bit. So what happens here is that, okay, so this is the other side of my equation and this is the positive side. I'm now going to solve for omega. So for the uppercase, this is easy, just substitute. You will get a bandwidth of this. So this is the upper bandwidth. So this is the right side, the bandwidth. And for the left side, you actually use this equation. So since it's the left side, the safest thing that to pick is the minus sign for this symbol. So if you use the RP1 squared form, which is this plus 1 minus this fraction, you will get this quantity here. This is the left side of your bandwidth. So what about the other root? So you will get the other root by using the plus sign for this function. And graphically, it will look like this. So this is the result of our positive side of the absolute value function. And then these two, this one to the left and this one to the right, is the result of the negative side of our absolute function. So these two alone define the safe zone. And just so happens that outside of the safe zone, there is another intersecting magnification value that is also equal to 1. So this is the greater of all of the roots here, and we can afford to ignore this. So once you get that, all you have to do is, okay, say that our safety value, safety bandwidth starts from this value, 1500 RPM, and ends with 1600. That is the answer to the safety bandwidth. So this is the root that never was. It's okay. Now you might be curious. Okay, so this example is only for case 1. What happens if the omega that you want to destroy is not equal to the primary system's natural frequency? So at this point, we are going to study the mass ratio and we're going to play around with beta. So when we play around with beta, we're essentially kind of moving this zero deflection point here. So let's see what happens if we increase beta here. If we increase beta, what happens is that your zero deflection moves from RP is equal to 1 to RP is equal to 1.2. Now, if we do it the other way, okay, so I want to reduce my beta. So that means you are targeting a frequency that is lower than your primary system's natural frequency. You will end up with this kind of behavior. So it's kind of fascinating. You don't really have, there is really no meaning to this widening here. Perhaps it's more useful because most of the frequencies that we want to operate in is usually greater than the primary system's natural frequency. So in application, you will probably see more of this rather than this. And that's good because if you lower your beta below 1, it seems like the threshold becomes tighter. Well, in comparison, even though you didn't really alter the mass ratio, your bandwidth still got wider because you moved to the right of the RP. So is that it? Yes, that's it. That is the end of our absorber lecture, and I hope you enjoyed your time listening to this. So if ever you have any questions, we do have our modules. There are fully answered problems there. I hope you practice them, and I hope you try to absorb what it means to essentially test out or feel out the equations themselves. So there are some problems that you might encounter related to absorbers. You may encounter them by filling out the equations, but they are probably not stated in the model. So I want you to exercise some creativity when it comes to absorber problems because um, there lies the fun with vibration observers. So if nothing else, thank you so much for listening and I hope you have a great day.